1D system. So I'm going to call this a 1D system, one-dimensional system. This is now two equations, two unknowns. We combine these guys, and I'm not going to make you do the algebra, I'm just going to give it to you, to solve out for V1 and V2, which were our unknowns. So V1, what? Well, we're the squares and stuff. I mean, for this part, yeah, you could drop all these 2's. That'd be fine. That would still be true. I just wanted to have, actually, then you'd have double the kinetic energy, which would be true. You can say double the kinetic energy in the system equals double the kinetic energy in the system afterward. It's fine. But anyway. So we can solve these out, and we get V1. So again, this is a, it's kind of a vector, it's just in a one-dimensional system. I'm going to leave the hat off. The positive is just going to be that way. If you get a negative value, it just means it's heading the other direction. All right? So I'm kind of leaving a vector in a one-dimensional system is kind of a odd thing to me, especially when you have the positive and negative signs. But the positive and negative side pretty much covers it. It means it's going that way or that way. So anyway, so everybody makes understand what I do with that and why I'm leaving a little hat off. So V1 equals U1, and this is an equation I would write down. Where are you? Minus M1 minus M2 plus 2M2 U2 all over M1 plus M2. And V2 equals U2 times M2 minus M1 plus 2M1 U1 over M1 plus M2. So say, given all this stuff, the U's and the M's, you can find the two V's. All right, this is just, these are combining that equation and that equation with some clever algebra substitution, which I'm leaving out. All right. And then, see here, yes,
To clarify, your masses are reversed in both of them.
from here,
And one minus.
yep. Yeah, I didn't screw that up, but sometimes. Let's get the signs correct. Get it. Yeah. Maybe again, just wouldn't work good. Just numbers. Yeah. Okay. And so this is all translational, like I was saying before. There's no rotational energy in this. This is for a one-dimensional system. You don't try and do this with a two-dimensional and three-dimensional system. It's definitely not happening. All right. So a couple properties we can derive again by doing more cleverness, but I'm going to be skipping. So I'm not going to expect you to do that particular cleverness. We can have some properties. So properties derived from the momentum and kinetic energy equations. So basically, we take that guy and we take that guy and mess around and we do some cleverness and point to some more stuff. We have V1 plus U1 equals U2 plus V2. So what this is saying is that, so the subscripts are for the typical specific object. So the velocity of the object beforehand, before the collision, plus the velocity of the same object after the collision equals the velocity of the other object before the collision plus the velocity of the other object after the collision. Okay? That's what this is saying. This is, again, this is for our 1D, still for our 1D system. Make sure you keep track this is still for our little one-dimensional system. And also, V1 minus V2 equals U2 u2 minus u1. And again, you have to do it in this order to get the signs to work out. So the velocity of the first object after the collision minus the velocity of the second object after the collision equals the velocity of the second object before the collision minus the velocity of the first object before the collision. Make sure you write down what the u's and the v's are. The u's are the velocities before, the v's are the velocities after. The subscripts are which object we're talking about. Subscript 1 is the first object, subscript 2 is the second object. Yeah? V's before, v's after. And so like alphabetical order. Something like that. And the one and the two are the which object we're talking about. So the ones
for
are
the subtraction, the way you have it written is the way we need to have it.
yes, it is.
But for the other one, doesn't matter.
That's true. It's addition, so it doesn't matter. Yeah, you can write the swap these, wouldn't matter. Swap those, wouldn't matter. But these it does. Okay. All right. Cool. Now I can show you my PowerPoint. A lot more stuff. More non-PowerPoint. Actually, that will probably run out of time. But we can do the PowerPoint for a second. So this is an elastic collision. The M is actually supposed to mean the mass. So these are two objects with the same mass. And so you got the blue one's at rest initially. The black one's coming in with a velocity v. And it's actually supposed to be v, like a quantity. Quantity v. So some of these later ones will talk about like a third v or something. So it comes in with quantity v, and then it stops. And the blue one exits with quantity v. And this is the only possible way this can be with an elastic collision to satisfy momentum, because momentum is mass times velocity. So we need m times v as our momentum coming in. So this thing is mass m, velocity v. So that means the total system, this is a closed system with no external forces. This is the kind of thing we're talking about, okay? You got these two objects, there's nothing else acting on them. And so the total system momentum is this guy is m times v. So velocity of m times v of this one, except this one's at rest. So the v here is 0. The initial velocity of this guy is 0. So it has no contribution to the system momentum to begin with. So after the collision, we still need m times v for our momentum. And we do. So we got that guy. M is going to v. So our momentum, conservation of momentum is satisfied. And that's always satisfied, even with inelastic collisions. Like if you have an inelastic collision where some of the kinetic energy is lost to heat, sound, whatever else, momentum is still conserved. Momentum is flat out conserved for a closed system. Kinetic energy? Maybe. If it's elastic, yes. If it's not, no. Momentum always is. So then we also have to satisfy kinetic energy for this. This is an elastic collision. So in this one, no kinetic energy is lost. So here our kinetic energy would be 1/2 mv squared coming in. This guy has no kinetic energy on this one. It's all on this guy. It's 1/2 the mass times velocity squared. This one's still 1/2 mv squared. So kinetic energy is conserved. So this is the only possible solution to this. So this is like when you shooting a play pool, and you hit it dead on. That's why the cue ball stops. It's pretty close to an elastic collision. You hit it dead on. All that momentum and energy is transferred to the other ball. Cue ball stops dead cold, like that. All right. Everybody's played pool, right? Yes.
Is that because they weigh the same?
Yeah. It's only because they weigh the same.
We call it a little bit smaller than the rest of them. They weigh the same.
Yeah, so this is with the wing saying, all right, next one.
The
same deal. They're two separate things. We'll talk about the top one first. So here, what's our momentum? We have m times v in this direction, so that's mv. And then this guy, before the collision, is minus mv over 2. I'm saying v is positive that way, negative that way. Alright? So this is a vector, so it has to have direction or momentum. Alright? So we have before the collision, we've got, for our momentum, we have mv for that guy, and then we have to add the other one, and it's headed the other direction, so it's plus a minus, and it's supposed to be going how fast here? V over 2. V over 2m. So that's our momentum. This is momentum. I need to come up with an abbreviation for momentum. So that's our momentum. Does everybody see where, okay? And the m and the v are the same. So we have 1.5 Vm. It's capital M. Mom? Yeah, mom works for me. Okay, so this is our momentum beforehand. It's 1.5 Vm. No, 0.5 Vm. Because we have the mv minus half. So it's 0.5. Now afterward, what's happening? Afterward, we got, say this is going to start with the black one again. It's going this way at v over 2. So I have minus v over 2m. That's the black one. And then the other guy is just vm. So again, I can add those up, and I still get Vm over 2 equals 0.5 Vm. So our momentum is conserved in this first collision. And so now if we want to do some kinetic energy. So this is all mom. Now the kinetic energy side of things. So our kinetic energy of the black one coming in is mv squared over 2. So we have mv squared over 2. So now this is the scalar quantity. There's no direction. This thing, the blue one, that's not negative kinetic energy. It does not have negative kinetic energy. There's no such thing as negative kinetic energy. Okay, its direction may be negative, but we're going to square it so that goes away. So we're going to have its initial velocity is v over 2. We're going to square that. So that's going to end up as v squared over 4. Did we get what they did there? V over 2 times v over 2 is v squared over 4. Right? Times n. And then we're still going to divide by 2. So that's our total kinetic energy. And so how much do we have? So this is m over 2 times v. I should figure this out beforehand. And this is m over 8. So it's actually 5/8. I think this is 5/8 v squared. I think that's right. And then so now afterward, well, I'm not going to redo it because it's still the same thing. We got one of them going at v, we got one of them going at v over 2. Which is the same thing we had before, but just the directions are switched. So the kinetic energy remains the same. Does that make sense? Why am I going to redo the equation? Is this the same basic deal? Beforehand, we had one going at v and one going at v over 2. Afterward, we still have one going at v and one going at v over 2. So pretty clearly our kinetic energy is conserved. Now the other one. Everybody understand this? So this is how we're using these two quantities, kinetic energy and momentum, to figure out what's happening with this. So this guy, this lower one. So our momentum, to begin with, before the collision, we have mv for the black one, and we have mv over 2 for the other one. Okay, so that's our, this is mom. Okay, and that needs to equal what we got afterwards. Now afterward, the black one is going to be over 2. So we have mv over 2. And the blue one is going mv. So we're good. Momentum is conserved. We're happy. Kinetic energy. So I think this one again is going to be sort of obvious, so I'm not even going to write it out. Because beforehand we have one mass, one mv, and we have one at mv over 2. And that's the same thing we have afterward. They just swap roles, which one is going to speed. Okay, when you have things of equal mass, it gets relatively easy. When they aren't going to be equal mass, it's a little more complex. So does everybody see why I'm not bothering to write out this time why the kinetic energy is conserved here? Okay.
Yeah.
But there are other ways to do this. So what do we have right here? This is a total of 1.5. This equals 1.5 mv. That's our momentum. So let's say another solution to this that would satisfy momentum would be these two guys come in and then they continue on together. And it just so happens I have a little video of such a thing. They go like that. So what happens is we've lost kinetic energy. So in this one, our momentum is still conserved. Because right here, what's our momentum? mv. Our momentum is mv, because the blue one's at rest. And afterward, we have going together, so it's v over 2, but then both 2m. Okay? So here, our momentum is still satisfied. But if we do the kinetic energy of this, this is going to be 1/2 mv squared. So beforehand, ke, before, it's, so we have one thing moving, it's just mv squared over 2, 1/2 mv squared. But afterward, what is it? We got 2m times v over 2 squared over 2, which equals, so those cancel out, and we end up with what? mv squared over 4. So this is after. So our momentum's we're still obeying our momentum. But because these guys didn't bounce the way they did in the elastic collision, this is perfectly inelastic. This is the maximum amount of kinetic energy you can lose. You can't lose any more, because if you were to try to lose any more, you wouldn't satisfy the momentum equation. The momentum equation is a flat out law and must be obeyed.
What sort of situation would you see something like this?
Water on a windshield.
Yeah.
Think for anything where there's like no bounce to it, like two pieces of clay maybe running into each other. Okay, they're not going to bounce. Or like, say a relatively elastic collision, is I take a basketball and I drop it, it's going to come most of the way back up. So it's not perfectly elastic. If it was perfectly elastic, it would come precisely back up to the same height. And we're going to get to dropping balls here in a little while. Whereas if I drop a piece of clay, it's not going to bounce. Momentum is conserved because the Earth moved a little bit. All right? When it hit, the Earth picked up a little bit of speed, keep the momentum constant. All right? Or your two chunks of clay hitting each other, or I don't know why this is here. Probably goes through his nose. We're playing two of them. Okay, they come together and they hit. They go along together. Momentum is conserved just like this. But with no bounce, we're going to lose kinetic energy. And I'll leave it at that. So study for the test.